Um, Thank you. We are starting the session. I'm offering Maksuda Khanam to start this session as she is the host of this session.
Thank you, Mr. Jahil Khandekar. Welcome everyone to this free online flight course, Exploring Ocean, Explore the Planet Earth 2, organized by Octophin, a platform where ocean-loving students from different places and platforms are working for raising ocean awareness by spreading ocean knowledge. We Octophins are working towards an ocean-aware planet. We deeply believe that no one can change this world alone, but together we can make this a better place, a better planet. Assalamu alaikum, this is Maksuda from Octophin. Hope you all are safe and sound in this pandemic situation, and hope one day we will overcome this situation. Roger says that we know less about the ocean's bottom than about the moon's backside. Do you know how Earth and oceans are formed and how ongoing processes may change them in the future? By the geoscience of ocean, you can know about this. Geological oceanography is the study of Earth beneath the oceans. It involves geochemical, geophysical, sedimentological, and paleontological investigations of ocean floor and coastal margins. Nowadays, a special GPS system is used to map the seafloor and underwater features. Today, we have our fourth lecture titled Knowing the Geoscience of Ocean. This lecture will be taken by Honorable Professor Aftab Alam Khan. He has done his PhD in Applied Geophysics from Indian School of Mines, India. He has retired from Dhaka University in 2017. Recently is serving as professor and head of the Department of Oceanography and Hydrography in Bangabandhu Sheikh Mujibur Rahman Maritime University, Bangladesh. He has 70 research publications and more than 50 conference paper and project articles. He has received Best Paper Award from Indian Geological Congress in 2013 and Dean Award from Dhaka University in 2016. He has 4 books in his credit. His recent researches focuses on sea level and climate change, geo-environment and pollution. No more talks. I am handing over this session to Mr. Aftab Alam Khan. If you have any question during the session about the lecture, you can ask us in the chat box. And if you are seeing the recorded file, you can ask any question in the comment section. We will try to answer. So hope for the best. I am offering Mr. Aftab Alam Khan to take from here. Please, sir.
Thank you, Madam Maksuda. Let me open my presentation. Uh, Probably have to open it from the beginning. Well, can everybody see my presentation, the slide?
No, sir, there is a problem with the share screen.
Oh, okay. Share, where is the... Okay. I think now it's all right. Yep.
Um, yes, sir. Now we can see.
Okay. Well, everybody, today's topic is knowing the geoscience of the ocean. That's quite interesting, as well as quite quite I would say complex topic, which needs the knowledge of multidisciplines. But I'll try to present my this talk in a very simplistic way, so that all we can in fact receive the message through this presentation. Well, my topic, as you know, the knowing the geoscience of the ocean. And to know an ocean, we need to know the genesis of an ocean, how the ocean has formed, from where the ocean has come. That means the formation of an ocean. An understanding of the genesis or the origin of an ocean, we need to know the knowledge of the formation of a solar system, because the Earth, where the ocean occurs, that is, Earth is in fact is one of the planets, one of the 8 planets in the solar system. So the Earth is one of the 8 planets in the solar system that formed back in 3.5 billion years. Sorry, 13.5 billion years. So 13.5 billion years back, the solar system started to form, where Earth started to emerge. There are 4 out of these 8 planets. There are 4 gaseous planets and 4 rocky planets. So Earth is one of the rocky planets. But the difference from the other 3 rocky planets is that Earth has the water and no other, or ocean. No other 3 rocky planets have any ocean or any water. So it is the only planet in the solar system that has the Earth. In fact, it has 2/3 surface area covered by the water of the ocean. Now, how we can describe Earth, or how we can see Earth? Earth is a dynamic planet. Every particle, every moment is in motion. So it's a very complex dynamic planet that we'll have to keep it in our mind. The visible Earth, which we see, has 24 hours and 365 days, anti-clockwise spinning around its own axis, and rotation around the sun, respectively. So the invisible Earth, the visible Earth has 24 hours and 365 days, anti-clockwise spinning around its own axis, but invisible Earth, which is the interior of the Earth, also a dynamic one. So a journey to the center of the Earth, if you make a journey from the surface of the Earth to the center of the Earth, then you will find many interesting zones inside the Earth, and very all of them are in motion. So the thick chamber, that the invisible Earth, which is the interior of the Earth, also a dynamic one, and the thick chamber between 2,900 kilometers that means from the surface of the Earth at a depth of 2,900 kilometer up to 5,200 kilometer. This zone is characterized by 4,500 degrees Celsius to about 5,500 degrees Celsius liquid iron and nickel. So you have around how much? 2,300, that means 2,300 kilometer thick zone inside the Earth has 4,500 to 5,500 degrees Celsius liquid iron and nickel. That's in motion. That's as the Earth is spinning in 24 hours, anti-clockwise spinning from west to east. That's why we can see the sun to rise from the east, and Earth is rotating around the sun in 365 days. So this motion is in fact keeping we call the outer core inside the Earth is in motion, and that is having temperature 4,500 to 5,500 degrees Celsius, incredible high temperature zone. So now the Earth was, I would say, about, in fact, Earth was formed here. Just a minute. Earth was formed
Hello, sir.
yeah, I don't know what happened.
Sir, your screen sharing is off. Please, you can start another time.
Yeah, okay.
Again. Sir, is there any network problem? Sir, do you can hear me?
Yeah, I can hear you, right. Just a minute.
The screen is sharing.
Okay.
Yes, sir.
Okay. So as I was talking, this Earth was formed about 4.5 billion years. Here, probably, yeah. You can see here, the Earth was formed 4.5 billion years ago by the process of accretion, when entire Earth was molten, having temperature about 5,500. So the initial Earth was completely molten. It's a very high temperature iron and nickel, everything were very much molten. So nowhere you can find any hard surface or any habitable surface. So that was the situation back in 4.5 billion years. Then Then with the heat radiation into the space, primitive crust started to form around 3.5 billion years ago. And around 2.5 billion years, the primitive crust became stabilized and distributed sporadically. Now we can see here that the white patches, the previous slide, which I showed you, that absolutely molten, all around the earth, there was no hard surface. Then this was the condition back in 4.5 billion years. But around 3.5 billion years, the primitive crust, you can see the white patches. These are the sporadic hard cover started to emerge by radiation of heat. By radiating heat into the space, they started to form hard part at the surface sporadically. Then this process continued for about 1 billion years, and around 2.5 billion years, we could have, in fact, the Earth could have the solid surface part, which started to get stabilized. That means the hard part of the Earth surface could emerge and got stabilized around 2.5 billion years. And at that time, the hard part of the crust was made of this element, this silicon, 27.7%, oxygen 46.6%, aluminum 8.1%, sodium, calcium, potassium, magnesium, iron. So all these chemical elements in the primitive in the crust we could get. Then so the formation of continent and ocean, the story goes like this. The sporadically distributed primitive crust, as I showed you, then started assembling by the process of collision. So the sporadic hard part of the surface started assembled together, and this is the time when intracrustal collision, that means the solid part, they started colliding each other among themselves, and the crustal composition started to change, and the initial crustal composition or rock, the hard part, crust, which was the basalt, that converted to some part of the basalt converted to granite. So in this way, we could have in the entire Earth's surface composed of oceanic crust, that means the basalt, and the continental crust, the granite. So emergence of all the continents thus began with dominant rock composition granite and new ocean with dominant rock composition basalt. Thus the stabilized crust has undergone several times the crustal separation and crustal amalgamation. So the stabilized crust, since 2.5 billion years, they started to separate. Again, they amalgamated. So this was the this is by the process which is known as plate tectonic. So in that process, the amalgamation and the separation of the crust, the hard part of the Earth surface, started to undergo separation and the amalgamation. The most recent crustal separation occurred back in around 185 million years, when the Gondwana supercontinent broke apart and the continental fragments started to drift away from each other. So this can be very simply you will be able to understand by saying so as the continental fragments drifted away from each other, the gap between them was filled by the molten material erupted from the inside Earth, known as magma chamber, through the overlying mantle. The newly formed crust became the floor of the ocean, and the following diagram depicts the Earth's interior. You can see here, so far explanation which I gave, now it will be very clear to you that initial stage the entire Earth was molten, and that is around 4.5 billion years. Then by heat radiation, sporadic crust at the surface started to form, that is around 3.5 billion years. Then the surface with hard part could form around the globe, around the Earth, back in 2.5 billion years. And since then, the number of times the hard part of the surface of the Earth got collided and also separated. This is the separation. They're going away from each other, the hard part of the crust, and here they are coming and colliding each other. So this is a tectonic process, plate tectonic process, but this is a very thin part of the entire Earth's inner zone. So in Earth's inner zone, if I consider this as a center of the Earth, then the radius from the surface is 6,378 kilometers. This is the radius of the Earth from the surface to the center of the Earth. And the Earth crust here is only 45 to 100 kilometer thick. So it is absolutely thin layer of the at the surface of the Earth. That is the hard part, and that we call the crust. Below the crust, you have entire zone up to 2,900 kilometer, the mantle. But this mantle is not solid. It's a zone where the material is a semi-solid plastic. It is the plastic material, and below this 2,900 kilometer depth, you have the outer core, which is absolutely molten, and that is your magma chamber, and that is occurring at around 5,500 degrees Celsius. And below that, from 5,200 kilometer to 6,300 by 400 kilometer, you have the inner core that is solid. So this is the interior of the Earth, and this is the diagram which depict the interior of the Earth, where inner core, outer core, mantle, and it is a very thin crustal layer. Now, about the Pangea and Sea of Tethys. Now, this crust, this crust, upper layer of the hard part, this undergoes several times the separation and collision. In the separation mode, you can have the molten material coming through the interior, and it is pushing the continents away from each other and filling the gaps with the molten material, newly emerged molten material, and that is forming by solidification the base of the new ocean crust. So new ocean crust can occur when there is a separation between the crust and the ocean. The ocean can close when they collide. If these two collide, then this ocean will be closed. So the opening of an ocean and closure of an ocean depends on the separation of the continents and the collision of the continents. So at the beginning of the age of dinosaurs, about 250 million years ago, the continents were together. All the continents were together and as a single supercontinent, which you call Pangea. And around 165 million years back, supercontinent Pangea slowly broke apart, forming Sea of Tethys between Gondwana and Laurasia. Around I can't see here, 85 million years back, Gondwana land broke and collided with Laurasia. India, a fragment of Gondwana land, also collided with Eurasia. Fragments of Laurasia and Sea of Tethys between India and Eurasia got close since 65 million years. Sediments deposited in the Sea of Tethys got squeezed, exhumed, and uplifted, forming present-day 2,400 kilometer long Himalaya range full of Tethian sediments. What is happening? Okay. So as I was telling that back in 250 million years, the entire Earth, all the continents, Europe, which we call Eurasia, North America, South America, Africa, Antarctica, India, and Australia, all these continents were together. That is back in 250 million years. And they formed a supercontinent, which is known as Pangea. And all the other region were Sea of Tethys. There's a sea, the ocean, which we call Sea of Tethys. And the crust of the continent are different than the crust of the ocean. Ocean crust or the ocean which is lying over the crustal composition is different than that of the continent lying over the crust. So the two different crust type you can see in the continents, which is a granite, and in the ocean, which is a basalt. So now the entire Earth, from here you can see that Earth, 2/3 of the surface area is covered by ocean. Only 1/3 is covered by your continents. Now this is the situation back in around 250 million years, and where you can see all the continents are together and all is the ocean. Then around 165 million years, they started to move away from each other. You can see the gap started to coming up between the continents. Now you can see the South America and North America is moving away from Europe, Eurasia, and Africa, and Atlantic Ocean is started to coming up. Then you have the Sea of Tethys here, other Sea of Tethys, those were now, is going to be closed. In fact, with time, it will be closed and new ocean will form. Now here you can see the more separation has taken place. Australia has moved away. India is coming to nearer to Eurasia, and new ocean is emerging, which is now Indian Ocean. And Sea of Tethys, which were earlier, it is now going to close. So this is the I think this is not the correct one. Okay. This is some animation that how the continents are moving and how they are colliding each other. So it is not very. You can see this one. This is when Gondwana land started to break. I'll tell you now. Now, this is from this position. Now the continents are moving away from each other. So Atlantic is coming up. Sea of Tethys is going to be closed. New Indian Ocean is coming up. Okay. So this particular process, and you can see a lot of islands and fragments and all these crystal blocks are emerging and being destroyed. So this is a continuous process is occurring in the earth since the inception of the earth back in 4.5 billion years, and it's continuing, but in a much slower rate, much slower rate. This is the animation which depict that you have molten material, how molten material comes through the crust. This is the primitive crust. So through primitive crust, the molten material comes and it pushes the continents away from each other, and the gap is filled by the molten material, and then molten material is solidified, makes the new ocean floor and new ocean. You can see here, that is the creation of the new ocean. This is the creation of the new ocean, where you can find the new ocean being created, and this is the closing of the ocean, how the when the two plates, two crustal blocks collides, then the ocean started to close. And you can see here, this ocean is slowly closing up. Here is the continents is pushing towards the ocean. Now this is the process which naturally occurs, that the plate, when it collides, it goes beneath the continent, and as it goes down to the mantle or deeper zone, there it melts, and when it melts, it produces molten material. That molten material, it can come through the continent and it can emerge as a volcano. And so volcanic materials you can find in the surface, and which can give rise to the volcanic chain or the volcanic mountains in the surface. Now, in a 2-dimension, you can see that this is the present situation. You have the North America and South America, and you have the Antarctica in the South Pole. Entire this is which is a continent, Antarctica, and this is your America, North and South. This Africa and Eurasian, and India, Australia, and Arabia, and this Sunda plate, Philippine plate. All these plates are, these are the crustal block. These are the very thin compared to the radius of the Earth, very thin surface, hard part of the surface of the Earth, and these lines are the lines along which, from where the continents have moved away. So these are called the mid-oceanic ridge. So from the ridge, all this ridge are the are the initial location of the continents, and then they started to move away from. And there are various terms which is known as your triple junction. Here is a you have this ridge, one ridge, two ridge, and three ridge. The three ridge meeting place in this is your triple junction. From triple junction, the continents, India has moved away, from Australia has moved away, and your Antarctica also somehow moved away. So these are the plate tectonic process, which we don't need to know much in detail. But this is the present situation where the oceans are characterized by prominent, all the here is the Indian Ocean, here is the Atlantic Ocean, here is the Pacific Ocean. So all the oceans have your dominant mid-oceanic ridges, and these are the elevated floor of the ocean, is where high temperature molten material is emerging in not everywhere, but in many part of the ridge. Your molten materials are coming up, and this we call the ring of fire. That means which is going through the through this Pacific rise all the way to Japan and, oh dear. So ring of fire, that means very continuously you have all the active volcanic chain around the ring of fire, which is in Philippines and all these places, Japan and this Pacific rise. So this is we call ring of fire, and not only volcanic eruption, but also you have the very earthquake prone zone here, and you have the Hawaii I mean island, Hawaii, which is a very active volcanoes are there, is located here in this Pacific Ocean. Now it's just a cartoon that shows that how molten material it comes up. So before coming through the interior of the Earth, it can the crustal block can be affected in various ways. So they can form reef basins, they can all these things. So they can form new oceanic crust, and continental crust can go away, and you have the definite very prominent movement of the molten material as a convection current inside the Earth. Now this is your Sea of Tethys, and this is India, and then this is the present time where the Sea of Tethys has been closed, but in some part it is the residual Sea of Tethys are there, and you can see the Himalayan mountain belt, 2,400 kilometer, this east-west elongated belt here, which has formed. And this Himalayan belt is the source of the sediment supply to this Bay of Bengal. Now, Bay of Bengal has emerged already, and the formation of the Bay of Bengal has started sometime around 118 million years, and India is a quite I mean same time as the Indian Ocean has started to form. But as initially the oldest ocean in the oldest ocean basin in the Bay of Bengal and in the Indian Ocean as the Western Basin, which is located here in our Bay of Bengal western margin, which was located in somewhere here. So that was the first ocean basin to appear, that is in 132 million years. Okay, this is the present day Indian Ocean, and you can which has completed its journey, and it has formed a long Himalayan belt here, and this is your my country, Bangladesh, and this your Bay of Bengal, and this is the Indian Ocean. And Indian Ocean, you have distinct your ridge, three ridges, mid-oceanic ridge, one here, and one here. And this is the meeting place. Here, the India was initially, and Australia also was here, and then it started moving. And this motion of the Indian plate from here to here is a guided. In fact, this is the guided by two main driving line. That is, one is here 90 east ridge. Another is a mega shear, is a slip plane. From here, the crust has moved to this place, and this is your Chagos Lakadweep. These two driving line has made the India to move from this triple junction to the present position. And this is the ocean feature in the Bay of Bengal and also in Indian Ocean. These are the ridge, this is the triple junction, and this is your 90th ridge mega shear. This is your Chagos Lakadweep, and this is your Bengal, Bay of Bengal. And in the Bay of Bengal, the most prominent feature, you can see the swatch of no ground here, which I will show you afterwards. And this swatch of no ground is a deep sea canyon, and it has its role in the Bay of Bengal is very very prominent. Well, this is your Indian Ocean, this summer wind, and which flows, and in fact the direction has not been changed. It's from the very long time, the same wind motion is continuing, and they carry the atmosphere. I mean, they carry the moisture from the Bay of Bengal, and can generate rainfall in this region. And so the sediments which I was talking about from this Himalaya range, the sediments which are coming through the Ganges and Brahmaputra. There are two major rivers, and another one is small here, Meghna. So these two main rivers are the main transporting agent of the sediments from Himalaya range, and these sediments are coming through through Bangladesh, through the Ganges Brahmaputra river system, and it's making a delta, very largest, one of the largest delta in the world. There's a GB Delta, we call it GBM, Ganges Brahmaputra Meghna Delta, which is formed, and the sediments which are coming through this region and depositing the sediments in the basin in the Bay of Bengal and forming a delta. Now this delta, in fact, the present coast is here, but this is about 12,000 years construction. So back in 12,000 years, the coast were somewhere here. Then sediments started to pour in here and being deposited. Then in some later on, then it the shoreline progressed to the south, further south, and present position. So this process of shifting the coastline from last 12,000 years has made this delta as a prograding delta. Means this delta progradation, that means the delta is advancing, and since delta is advancing, your sea is retreating. So your land emerging, your delta is extending further south, and your lot of islands are coming up, and it has attained the present situation, present position like this. But still, this process is not end. I mean, this is going on. Now, the present prograding GBM delta, which present prograding GBM delta with influx of sediments in the Bay of Bengal, helping land acquisition in the entire Bangladesh coast and Bengal deep sea fan building. Now, you can see this is suspended sediments which are in the suspension in the Bay of Bengal, and there are all are is extended quite deep in the sea. Now, this process was earlier. So this sediment influx, when the coast was here, the same kind of sediment influx was there. So the sediment started to pour in, then started to deposit in the floor of the sea, as it is being deposited now, and coastal and the coast started to move, started to shift, or started to prograde towards south, enhancing the land and shifting and pushing the sea farther away from the land. Now, these suspended sediments, as I told you, that here you have the swatch of no ground. This is a continental shelf, and here's the swatch of no ground and deep sea canyon. The deep sea canyon is very very deep, in the sense that the continental shelf has a this is a continental shelf. It has the water depth maximum from 20 meter to 200 meter. But the swatch of no ground, which is located somewhere here, it has about 1,800 meter water depth. So the suspended sediments, about more than 2 billion tons of sediments every year is coming, out of which about 1 billion tons of sediments are going through this swatch of no ground into the deep sea and making a new deposits, which is known as Bengal deep sea fan. And this is the mechanism by which the sediments can move in the deep ocean. And you can, if you consider this as a deep sea canyon, the swatch of no ground, the sediments coming in through these, and it is going coming out. When it is entering, the velocity, the entry velocity, and when it is leaving the canyon is 9 times greater. So 9 times greater velocity, the suspended sediments is coming out of this swatch of no ground, and it's spreading like a fan. You have all you know about the geometry of a fan. So hand fan. So fan and the geometry, fan geometry, you can the sediments are distributed, and then slowly the sediments are deposited in the floor of the sea. So as I was telling here, so this is your continental shelf. The entire suspended sediments are of which about 40%, that's 1 billion tons, is going through this swatch of no ground, and it's in the deposited in the fan. And so they have made a fan which is known as Bengal deep sea fan up to Sri Lanka. So it's a huge fan has been deposited in the Bay of Bengal, and the sediments thickness of the fan is around 4 kilometers, but total thickness of the sediments in the Bay of Bengal is around 12 kilometers thick. Well, this is a cartoon which signify how the Bay of Bengal has opened up. So this Bay of Bengal, it was, I mean, in fact, the India, because in the Bay of Bengal is very much linked to the movement of the Indian plate. So Indian plate was in the triple junction. At that time, the initial Bay of Bengal, this is the western basin of the Bay of Bengal. So western basin was also there. So as India moved, this basin also moved along with India. But the other part here, I mean, there is another ridge which we know, we call it a 85 east ridge. Beyond on the eastern side, the eastern basin of the Bay of Bengal, which is the new basin than the western basin. And the opening of the basin, as it moved, the plate, as it moved from the south to the present position, this is the driving line. So you can see that here you have the crust which has opened up. I mean, newly formed crust from the below. It has helped to open or move the Bengal Bay of Bengal and to form the Bengal deep sea fan. So this is not very important for you to understand. Leave it. Then this is the Bay of Bengal situation now. You can see the very prominent swatch of no ground, and you can see very prominent 90s ridge, and you can see 85 east ridge, and you can see the western basin, and you can see the eastern basin. Sediment thickness in the eastern basin is less than the sediment in the western basin, and rock displacement, or means the high density material is much in the eastern basin than in the western basin. This is also the evidence of how the Bay of Bengal has opened up. So these are we call magnetic anomaly number, which signifies that signify the opening of the Bay of Bengal. So Bay of Bengal has opened up, and that's the sea floor has sprayed it. Now this is Bay of Bengal again from the sediments, suspended sediment through the swatch of no ground. It has entered into the deep sea region, and there are a number of submarine channel. There are a number of submarine channel, major channel, through which also the sediment transportation has occurred in the deep sea fan region. About georesource of the Bay of Bengal. Bay of Bengal is very potential from hydrocarbon point of view, and discoveries of gas in the Krishna Godavari basin in India, and then oil and gas field in deep water Krishna Godavari basin, and discovery of the Mahanadi basin in India, and the discovery of large deposits in Sioux gas in Rakhine basin of Myanmar, all exhibit strong evidences in favor of new future discoveries in the deep water basin of Bangladesh. So we are very much hopeful that if we continue to carry our study and research in the Bay of Bengal, we'll be able to discover oil and gas deposit in the Bay of Bengal in future. This is one small structure which we know in the Bay of Bengal, in the shelf, continental shelf, which is known as Sangu, where we could get 0.8 TCF gas, but another big structure which we missed gas because of the wrong drilling location. However, that will be solved in future. About the hazards, in the Bay of Bengal, normally there are geological hazards like your volcanic activities, mud diapism, mud volcanism, slope instability, submarine landslide, turbidites, natural gas hydrates, shallow water flows, active fluid seepage, seafloor pockmark formation, earthquake, tsunamis, sea level change. These are the hazards for the ocean and sea-based hazards we frequently encounter globally. But in Bay of Bengal, we are not much prone to the geological hazards, but we are prone to atmospheric hazards like cyclone and storm surge. But geological hazards is not very much. But there are some earthquake occurrence are there. There had been one impact of the tsunami when 2004 Sumatra tsunami or Banda Aceh tsunami occurred. That tsunami has a not effect could not put any massive impact, but some kind of psyche, that means some sea level change, water level change has encountered. So that's not very very prominent. But other, like your slope instability, that's quite there. Mud diapism, mud volcanics, this is there. Turbidites are there. So these are the few geological hazards we may encounter in the Bay of Bengal. Regarding sea level change, uh, there is no evidence of sea level rise in the Bay of Bengal. Rather, sea level uh, is going down. In fact, sea level is remaining static, stable, but it is moving away from the. I mean, coastal belt is going um, is prograding towards the sea, and there is no definite proof that the sea level will rise and our one-third area of the coast will be inundated. There is no proof. I can show you. Um, uh, I can show you this. This is some geological hazards which are you can encounter, like overpressure, diaparism, some gas hydrate, and earthquakes are some earthquake, mud volcanoes. These are, but not very prominent hazards are there. But regarding sea level rise, which is now is very much in a hot discussion, that Bangladesh Bay of Bengal sea level will rise, and one-third area of Bangladesh will undergo submergence, and about millions of people will suffer migration or shifting from the coastal belt. These are all hypothetical. These are all very hypothetical, and nothing, no evidence has yet to be acquired. So now you can see here, as I was saying, that this is the shape of the Earth, and the shape of the Earth, you can see here that the equatorial region has a is a expansion or bulging, and polar region has a flattening, and this has caused due to the Earth's maximum centrifugal force along the equator and zero centrifugal force along the pole. So since you have the maximum centrifugal force along the equatorial belt, and all the Earth is full of water, two-third area is water, so the spinning of the Earth, anti-clockwise spinning, is this maximum centrifugal force is the water is bulged up in the equatorial belt, and that is dominantly between 30° north to 30° south. So, and as it is bulged up, you have the polar flattening. The polar has a depressed. Now you can see here that this is the polar region, and this is the maximum curvature, and the difference between the polar radius and the equatorial radius about 21 kilometers. That means the equatorial radius is 21 kilometers above the polar radius. That means this is the up the hill. So water will never move up the hill. So water from the polar region will never move to the equatorial region. Now, as it is said that the global warming will melt the ice, and that will add to the ocean, and sea level will rise. That is also not true, because you can see the 1980, the ice was here, then by 2005 it has melted, but it has not added any water because the same volume it has occupied. When it was ice, the volume the space which it occupied, when it melt, it reoccupied the same volume. So without it didn't add any water to the ocean. And you can see here that more than 90% of the ice in the ocean are submerged. So when it has occupied an space volume. Now when it will melt, it will occupy the same volume, and the surface, which is about above the ocean water, about 5 to 10% ice, this will melt, but this will not add to any significant water level rise, sea level rise. So this is one thing. And another thing, that the global warming, as it claimed that global warming will cause the thermal expansion of the ocean water. So that is also not true, because the ice, floating ice from the southern ocean, that's Antarctic, up to your 30-degree south, they will cool the surface water when they, because this ice surface ice, it will melt because of the temperature, warm temperature of the surface water. So it will be heat transfer, so that will balance, that will not add to the expansion of the volumetric expansion of the ocean water. Sea level will rise only or fall only if you have the oceanic crust. When it will subside, sea level will drop. When oceanic crust will uplift, sea level will rise. So that is the geological phenomena, and that is not expected in a human time scale. Another example in the Bay of Bengal, that 1997, this is one island, Nijhum Deep. No, sorry, Bhasanchar. Bhasanchar, it was just the island was just emerging. There's a trace, but by 2019, you get a complete island. Then entire coastal belt. This is your 1990. You 1990, you see the islands in the coastal belt, but in 2019, you can see the islands, how many islands it has come. So there are many other examples which can be given regarding the no sea level rise in the Bay of Bengal. And you can see from here, it is very much evident that the sea has moved away. That means sea level has shifted from seaward, oceanward, not the sea has entered landward for the last, at least for the last 12,000 years. Well, that's my end of the presentation.
Well, thank you, sir. Thank you for your informative session. Now we are going to the next session, the question answering session. I'm offering Akshan Kifayat to start the question answering session. Please, Akshan.
Thank you very much, sir, for your enchanting, informative, and prudent lecture. I believe the participants not only learned a lot from the session, but they also enjoyed the session to the fullest. Hello, everyone. My name is Akshan Kifayat Nripo from Octophin, and I will be your host for this question and answer session. Dear participants, I would like to remind you that due to the constraints of time, it will be impossible for us to pay heed to all of your questions in this session. But don't be disappointed because we will try to answer the unanswered questions of Q&A in the Facebook group Exploring the Ocean, Explore the Planet Earth. So please make sure that you are a member of that group. So without any more delay, let's go into the session. So our first question is from MD Tanvir Hussain. He asked, has the interior part of the Earth any effects on the ocean's geoscience? Awaiting your answer, sir.
Yeah, definitely the interior of the Earth, because uh, as you have seen that initially Earth was totally molten. Then with time, in fact, geologic time, you have got the surface, hard part of the Earth. There's a very thin layer, crust, and then from the um, uh, from the interior of the Earth, the molten material that must have that had emerged through the continents, primitive crust, and pushed away the primitive crust and open a new zone, and where the molten material could occupy the space, and eventually the molten material got solidified and made a new crust, and that new crust is the crust of the ocean, a new ocean. So unless and until you have the interior process of the Earth active, you cannot have the creation, formation of the ocean, and or the closure of the ocean. This is a continuous process in the geologic domain.
Thank you, sir. The second question is from Mr. Nibir. He asked to please explain the process of accretion physics. What are your thoughts, sir?
Accretion is a process where two particles can collide each other, and when it collides, they lose their gravitational field, and new particle is formed with the new gravity field. This is the process which the entire initial proto solar system was having. So the particle collision and losing gravity, and enhancing the particle size, then again colliding with another particle. So this process is the accretion process.
Thank you, sir. The next question is from Zannatu Adan Mim. She asked, what is crustal amalgamation? Awaiting your answer, sir.
Crustal amalgamation is the getting together all the crust, when initially the crust started to form sporadically, not uniformly. So the sporadic crust then started to amalgamate or accumulate each other to form a new crustal block. That is amalgamation. And separation, when the amalgamated crust are separated by some geologic process, then it is the separation or drifting of the continents. So amalgamation is the accumulation of the crust.
Thank you, sir. The next question is from Mr. Nibir. He asked, how and why does the tectonic process happen?
Well, there is a, as I told you in my presentation, that in the Earth's interior, there is a zone between 2,900 kilometers to 5,200 kilometers. It's a quite thick zone. That zone is known as magma chamber, where more molten magma or molten material is occurring. And that chamber, that zone is characterized by a infinite number of convection cells, couple convection cells. So convection cells can uh, convection cells, the opposite, one convection cell moves clockwise, another convection cell moves anti-clockwise. So they can bring the molten material from the interior to the outer part of the earth. And when it comes out from the interior, from that chamber, the overlying solid part of the solid layer starts getting affected, and the remelting of the crust starts. Then all other processes starts. Then the plates starts moving, and the motion of the plate is the plate tectonic process. And plate tectonic is a force, is a geological force, or the tectonic is a geologic force. Plate tectonic is a force or a geologic force generated by a plate. Okay.
Thank you, sir. The next question is from Mr. Akash. He asked, Professor, what happens as a result of crustal separation and amalgamation? Thanks in advance.
I told earlier this amalgamation, what is amalgamation and what is your separation. When crust amalgamated, they form supercontinent. When crust are separated, they form ocean. Okay, Akash?
Thank you, sir. The next question is again from MD Tanvir Hussain. He asked, by which component the ocean crust is different from the land crust?
Only the rock type. In the continent, you have the granite, which is acidic rock, and ocean is underlain by the basic crust, which is basalt. That is the difference.
Thank you very much, sir. The next question is from Afrina Binte Harun. She asked, is there any relation with uplifting of water in the ocean or cyclone with the semi-solid materials inside the crust when it pushes to come out in the crust?
No. I mean, if you take the example of a volcano, if any volcano occurs inside the ocean or under the ocean or under the sea, initially some water will be thrown in the atmosphere or thrown in the space due to volcanic eruption. But that will again will drop back in the ocean surface. But that will not change the ocean level or sea level. But if there is a tsunami, then for some time the ocean level can be much higher. And for tsunami, you must have an earthquake in the ocean bed, and ocean bed has to push up. So when the ocean bed pushes up, it can push entire water column of the sea or ocean upward. So that can move the ocean water with a higher velocity.
Thank you, sir. She again asked, is there any relation with formation of fossils and tectonic plate movement?
No. No.
Thank you, sir. The next question is from Fariha Tasnim. She asked, what are the roles of swatch of no ground in Bay of Bengal and why it is named so?
Swatch of no ground means there is no ground. We cannot find any ground in that canyon. That's why it's a swatch of no ground. The ground of the feature was not determined initially, and then it was named swatch of no ground. But it's a deep sea canyon. It's a like your gorge in the hilly region. If you have visited, when you see the gorge, it's a deep gorge. It's a erosional feature, but the erosion of the material occurs where there is a weak zone, and to have weak zone, you need some kind of tectonic force. So swatch of no ground is a combination of the tectonic and the erosional process.
Thank you, sir. The next question is from Mr. Sukumar. He asked, does any of volcanic explosion occur under the ocean?
Yeah, as I told you, Ring of Fire is very much ocean prone, very much volcano prone region where a lot of volcanoes are continuously occurring. Hawaii chain of volcanic chain, then Philippines, all these places the volcanoes are very much frequent. In our Bay of Bengal, such there is no such volcano, but in Andaman Sea you have mud volcanoes, the evidence of volcanoes, mud volcanoes. Yeah.
Thank you very much, sir. The next question is from Nayan Jyoti Roy Kanok. The question, does GBM Delta sedimentation have any correlation with ridges?
No. Which ridges? I mean, if I understand your question, ridge means the mid-oceanic ridges. If it is mid-oceanic ridge, your question is, then it is no.
Thank you, sir. The next question is again from Mr. Nibir. He asked, what is delta?
Delta is a depositional feature which is formed by the deposition of sediments.
Thank you very much, sir. The next question is from Nayan Jyoti Roy Kanok. And the question is, what is Bengal deep sea fan?
Bengal deep sea fan is another depositional feature, but the deposition, the geometry of the deposition is your fan type. The structure of the deposition is a fan. Okay.
Thank you, sir. He again
Akshan, can you tell me how many questions are there?
Sir, there are only two more, sir.
Two more. Okay, very nice. Thank you.
So the next question is from Noyanjati Roy Kanok again. What is SHWE gas?
Sea gas. Sea gas is a name of a place, name of a field where gas has been discovered.
Thank you, sir. The last question is, what is mud diapirism?
Oh, that's a good question. Mud diapirism is normally what happens in the ocean, the sediments which you get is known as shell. We call it a shell, the rock type, which is sedimentary rock. So the deposition which is made in the sea that can lead to the formation of a sedimentary rock shell. The shell characteristically is a rock type, a sedimentary rock type that has a high porosity. That means its percentage of pore space is much greater, but the pore spaces are not interconnected. That means it has got absolutely very low permeability. So during the deposition of shale, the pore spaces uh, are filled with the saline water, brine or saline water in the pore space, and they are trapped. They cannot move, escape with the deposition. They cannot escape. They remain inside the pore space because there is no permeability of the shell. Now the deposition continues. So as deposition continues, the shell pore suffers pressure, high pressure. As deposition continues more and more, the overburden pressure continues to increase. So when overburden pressure continues to increase, your pore pressure also continues to increase. So at some threshold value, the pore pressure is so extensive that it just come out as a intrusion, or it can is just explosion. It come out from the formation as explosion. So when it comes out, it brings the mud along with the explosion, and that mud is deposited in the path, in the avenues of the explosion. So that is your mud volcanism or mud diaparism.
Thank you very much, sir. Well, I only wish if the clock had ticked a little slower, but alas.
Thank you for your compliment. Thank you. Okay.
Yes, sir. Um, in the end, I would like to humbly thank Dr. Altaf Alam Khan for his time and patience. Sir, it was an honor having you with us, and I firmly believe that in our future endeavors, you will again grace us with your presence.
Okay. Thank you.
Also,
I wish you all the best.
thank you very much, sir. Also, thanking the participants for their time and patience, I would like to draw the conclusion of today's session here. Stay home, stay safe, and don't forget to wear a mask. Thank you very much.